All right, guys, we are recording. Let me go ahead and share my screen and show you guys what's in Schoology as we begin to go over the material for today. Okay. Excuse me. Okay. Okay, so we're in the fourth period. We're in the fifth 6 weeks. Today is March the 29th, and it is a Monday. Okay. So on today, we're going to be talking about projectile motion. Remember on last week, we talked about circular motion. On today, we're going to be focusing on the concepts behind projectile motion. And of course, on today is just basically just dealing with concepts. We're not going to be utilizing any math or utilizing any equations. It's just solely focusing on concepts. Now, what is projectile motion? Projectile motion is a form of motion experienced by an object or particle that is launched near the Earth's surface and moves along a curved path under the influence of gravity. So I'm going to say that again. Projectile motion involves a particle that has been launched near the Earth's surface and follows a curved path acting under the influence of gravity. So we're going to elaborate more on projectile motion today. I'm going to show you guys a few video clips. We're going to do a few examples from this PDF file. We're going to do a few examples as a class together. You guys don't have to write anything down. Just basically just pay attention. Be sure you're understanding the concepts, because as soon as we get done going over the concepts, I'm going to open up this assignment for you guys to complete. It is a multiple choice assignment, all multiple choice, 16 questions. And it deals with comparing various situations whenever we're talking about projectile motion. Okay, so that is the goal for today. Yes, Angelina, you heard that correctly. No math, no equations, just concepts. Are you okay with that? Yeah, it's just solely focusing on concepts. All right, guys. So let's see. Where do I want to begin? Okay. You and math need a break. I understand. You know, so even though I love physics, sometimes I need a break from physics. Just being honest. Um, all right. So now so projectile motion. Remember, I said projectile motion is basically any motion that resembles a curved path because it's acting under the influence of gravity. Let me show you guys what I mean when I say this. Let me play this video clip here, and just let us talk about a few important things. Okay. So now whenever we're talking about projectile motion, it is very important that you guys understand that whenever an object is moving through space, and it is a projectile, it's acting under influence of gravity, it's important to understand that you consider the x and y components of that motion to be completely independent of each other. I'm going to say that again. The x and y components of that motion are completely independent of each other. And this video clip here kind of demonstrates what it is that I mean. Guys, notice what's happening here. So we have this physics teacher in his classroom. This physics teacher is tossing a volleyball. And as he tosses his volleyball, notice how the volleyball starts off on this side of the classroom and it moves all the way to that side of the classroom. Okay. Now, I want you guys to notice off to the side here and along the bottom, the physics teacher, he drew a motion map that basically represents the motion of the volleyball in the x direction And here, this motion map represents the motion of the volleyball along the y direction. So hopefully everybody can see that. So again, we're dealing with two things here. The volleyball, it's moving in the x direction, okay, at the exact same time that it's moving in the y direction, okay. So it's moving in the x direction at the exact same time that it's moving in the y direction. Now, remember what I just said. It's important to keep in mind that anytime an object is moving through space, its x component is independent of its y component. In other words, what's happening in the y direction has no impact on what's happening in the x direction, and vice versa. Okay. Here's specifically what I mean as it relates to this particular example. Guys, I want y'all to notice something. The moment the volleyball comes out of the guy's hands, notice these snapshots of the volleyball right here along the bottom shows us the position of the volleyball in the x direction for specific moments in time. What do you guys notice? What do you guys notice about the spacing between the volleyball in the x direction? So what do you notice about the spacing? If you notice, the spacing appears to be pretty even. So guys, tell me in the chat box, if the spacing appears to be pretty even, what does that tell us about our velocity in the x direction? Anyone? Come on guys, we talked about motion maps before.
Can you say it again?
If the spacing is even between these balls here, what does it tell us about our motion? Is it
It's in a constant.
Is it constant
motion.
what?
Motion.
I'm
It's
looking
in a constant.
I'm looking for not a constant acceleration, but a constant what?
Speed.
Constant velocity.
Velocity.
Exactly.
Okay.
Exactly. Yes. Yes, Angelina. Thank you, Jeremiah. A constant velocity. Yep. So now it's moving in a constant velocity because of Newton's first law. Remember what Newton's first law says: an object in motion stays in motion as a constant at a constant velocity, assuming there are no outside forces acting on the ball. Now, because there are no forces acting in the x direction, again, assuming we are ignoring air resistance, there are no forces acting in the x direction, so the velocity stays constant in the x direction. But guys, let me ask you a question. Does the velocity of the ball stay constant in the y direction? What do y'all think? Yes or no? Does the velocity stay constant in the y direction? No, exactly. It does not. Why is that, Stephanie? Because what's happening in the y direction? What force is acting on the ball in the y direction? Stephanie, what force is acting on the ball in the y direction? Come on, guys. Y'all know this. Force. What force is causing the acceleration? What force?
Gravity.
Gravity. Exactly. Thank you. So the force of gravity is acting on the ball in the y direction. And so, yes, Angelina, because the force of gravity is acting on the ball in the y direction, that force causes the velocity to decrease as the ball goes upward. And then here, the ball comes to a stop briefly at the top, and then the velocity begins to increase as the ball goes downward. Okay? So we see that here. So the velocity decreases, comes to a stop, and then increases as it goes downward. Okay. So at the very top, the instantaneous velocity is 0 because it, and then as the ball begins to go downward, the velocity increases. Okay. So, but here's the important point that I want you guys to note here. The reason why the velocity stays constant in the x direction is because the force of gravity that's acting in the y direction, guys, that force has no impact whatsoever on what's happening in the x direction. The x velocity is completely independent of it. Okay, so that's very important that you guys understand that whenever we're talking about projectile motion, and of course we're going to elaborate more on these concepts in the coming days, but just something I want you guys to keep in mind. And let me stop sharing my screen here. Okay. Now, it turns out, guys, whenever you're considering projectile motion and you're considering the independence of x and y, it turns out that whenever you consider the implications of that, you get some very, very bizarre consequences. Um, uh, Let me give you guys a basic example of what I mean when I'm talking about bizarre consequences. Imagine for a second that I was outside and I'm in the middle of a giant soccer field. So there's there's no one around. I'm just in the middle of the soccer field, and I have this ball in my hand. Now, guys, just imagine that I'm running. I'm running as fast as I can um, through this soccer field. I'm running. Of course, I'm running at a constant velocity, but I'm running as fast as I can. Guys, imagine that while I'm running, I decide to take this ball and I decide to throw it straight up in the air. So just throw it straight up in the air as high as I can throw it. And while I throw the ball straight up in the air, I'm still running, and I'm just keeping my hand held out. Just keeping my hand held out while I'm running as fast as I can. Believe it or not, guys, that all I have to do is just keep my hand held out and just keep running at a constant velocity. I can guarantee that sometime later, that ball is going to fall right back in my hand if I just keep running at a constant velocity. And that will happen 100% of the time that I throw that ball up in the air and attempt to catch it again. Let me show you guys a video demonstration of what I mean by this, just to kind of get a visualization of what it is I'm talking about when I'm saying launching a ball straight up from a moving object. Let me show you guys a video of what I mean by this. Okay, guys, in this video clip that I'm about to show here, I want you guys to notice something here. This guy right here, his name is Professor Walter Lewin. He's a professor of physics. He used to teach at MIT. Right here, he has a cylinder attached to a cart, which is along this really long track here. Okay, now he's able to hit a switch and basically shoot up a golf ball from this cylinder, right? So there's a golf ball inside of the cylinder, and when he activates a switch, he shoots a golf ball, and that golf ball goes straight up in the air. Guys, I want you guys to watch what happens whenever he decides to launch to launch this golf ball while this cart is moving along this track. Watch what happens. Notice how no matter how hard he pushes this cart, this golf ball is guaranteed to land back in this cylinder after it is launched a few seconds later. So let's see.
Once we have achieved that the golf ball will come back there, then I'm going to give this car a push. And the moment that it passes through this switch, the golf ball will fire. So the golf ball will go straight up, as seen from the car. But it has a horizontal velocity, which is exactly the same horizontal velocity as the car. So the car, I like my hands. As the golf ball goes like this, the car stays always exactly under the golf ball. Always exactly under the golf ball. And if all works well, the ball ends up exactly on the car again. Let me first show you, otherwise if that doesn't work, of course it's all over, that if we shoot the ball straight up, that it comes back here. If it doesn't do that, I don't even have to try this more complicated experiment. So here's the golf ball. I'm going to fire the gun now. Close. Close. Reasonably close. Well, since it's only reasonably close, perhaps perhaps it would help if we give it a little bit of leeway. So, there goes the gun. Here comes the ball. And this is just in case. Tape it down. So as I'm going to push this now, give it a push, the gun will be triggered when the middle of the car is here. You've seen how high that ball goes, so that ball will go. And depending upon how hard I push it, they may meet here or they may meet there. You ready for this? You ready? I'm ready. Physics works. See you Wednesday.
All right, pretty cool, huh? Guys, let me ask you a question. If he had repeated this exact same experiment a second time, a third time, a fourth time, a fifth time, um, is that golf ball guaranteed to land in that cylinder 100% of the time, assuming it's launched straight up? Yes or no? What do y'all think? So if he kept repeating that experiment over and over again, is that golf ball guaranteed to land in that cylinder? What do y'all think?
I doubt it.
No, Jeremiah, it turns out it is. Yes, it will. And check this out, Jeremiah. I'm gonna say something that made this sound crazy. It doesn't even matter how hard he pushes the cart. He could push the cart and give it a very high velocity, or he can give it a very low velocity. In fact, this could be a really long track that's as long as that room, and he can push this cart to the other side of the room. I promise you, Jeremiah, that if he tried that experiment 100% of the time, that golf ball is guaranteed to land in that cylinder. Do you believe me, Jeremiah?
Yeah, you have a degree, so.
Well, just don't believe me because I have a degree. Just believe me because of the physics. Think about why they see us, Jeremiah. Think about what I just said about projectile motion. Okay. Let me remember the cart is moving along the x direction, right? But are there any forces acting in the x direction, Jeremiah? Are there any horizontal forces acting in this direction?
No, it's just going to the. It's just
No.
moving to the right.
Yeah, it's just moving to the right. There are no forces acting in the x direction. So if there are no forces acting in the x direction, what does Newton's first law say? Is an object in motion should do what?
Stays in motion.
Stay in motion at a constant velocity. In fact, the only force, and again, I'm assuming we're ignoring air resistance, the only force acting in this room is gravity. Okay, but gravity doesn't act in the x direction. Gravity acts only in the y direction. So, Jeremiah, think about this. The reason why that golf ball
The gun
lands
will be triggered when the middle.
the reason why that golf ball lands in that cylinder is because the moment he moves his cart, the moment that golf ball is released straight upward, the horizontal velocity of the golf ball matches the horizontal velocity of the cart. And that is true 100% of the time. 100% of the time. So look closer. Look. Notice how the ball always stayed under the cart. I'm sorry.
So he.
It's stayed above the cart. Excuse me. So, Jeremiah, if he had tried that exact same experiment a third time, a fourth time, a fifth time, a sixth time, if he had tried that experiment 100 times, guarantee that ball is going to land in that cart. Land
So
in the
he
cylinder
just.
attached to that cart. I'm sorry?
So he just managed to like track the distance of the cart rolling and the distance of the ball going high.
What I'm saying is the ball is going to always stay with the cart because there's no forces acting in the x direction. What's happening in the y direction has no impact whatsoever on what's happening in the x direction. I'm going to show you one more example, and it may make more sense with this example. Let me give another example. The point is the x and y components are completely independent of each other. Hold on, fine, guys. Give me just a second. All right, sorry about that, guys. I was answering a private question in the chat box. Okay, let me show you guys one more example of what I mean when I talk about the X and Y components are completely independent of each other. And hopefully this will kind of rid some misconceptions some of you guys may have. Okay. Okay, guys, in this video here, in this video clip here, I want you guys to notice there's a pickup truck driving down this road. And as this pickup truck drives down this road, if y'all can see this here, there's a boy in the back of this pickup truck here, and he has a ball in his hand. And while that truck is moving, he's going to throw the ball straight up. Now, guys, sometimes some students have the misconception that if they throw up an object on the back of a moving vehicle, some people have the misconception that that object goes straight up and then comes back down. Okay, so it goes straight up and comes back down. However, that's not the case. Watch what happens to the ball as it goes straight up. Notice its path is going to resemble the path of a projectile. In other words, it's going to have a curve to it. It's going to look like an arc. Okay, and guys, watch closely. Watch closely the path of the ball. The moment it's released from the boy's hand. Okay. I'm gonna play this in normal speed and then I'm gonna play it in slow motion. Okay. It's easier to see it looking in slow motion. So let's look at normal speed first. Okay. Let's look at that again in slow motion. Because it always helps to look at things in slow motion to make sense of what I'm referring to. Okay. So guys, look at the ball when it comes out of the boy's hand. Someone tell me, does the ball go straight up and come back down vertically, or does it follow a curved path? What do y'all think? Does it go straight up and down, or is it following a curved path? Look. Someone tell me in chat box. Look closely at the ball relative to the trees. Yeah, it's following a curved path. Exactly, Stephanie. It's called following a curved path. So, Jeremiah, can you see that as he threw the ball straight up and had his hands held out, the ball landed in his hands?
Yeah.
Yeah. Yes, Angelina, it is definitely a curved path. So, okay, let me ask you a question, Jeremiah. Right now, this truck is moving really slow. But what if that truck was moving really fast? And let's assuming we could ignore air resistance, like assuming there was no wind, no air resistance. Would that ball land at his hand if he threw it straight up, even if that truck was moving really fast? What do you think? Yes or no, Jeremiah?
I mean, yeah, would have to.
It would have to, because that's what the physics says. You're right, Angelina. You're right. It's definitely a curved path. Like I said, sometimes students think it's a straight path, but it's definitely a curved path. If y'all look closely. In fact, if you guys notice how the ball. Look closely, guys. Notice how the moment the ball is released, notice how the ball moves at the exact same velocity the truck is moving at. Can y'all see that? Like the speed of the ball in the x direction is the exact same thing as the speed of the ball of the truck in the x direction. Okay. So look closely, guys. So notice both the truck and the ball are moving in the x direction. But remember, guys, there are no forces acting in the x direction. Gravity only acts in the y direction. So since gravity only acts in the y direction, whatever's happening in the y direction has no impact on what's happening in the x direction. The two components are completely independent of each other. Completely. Okay. So in other words, the moment the ball comes out of the guy's hands, it's going to be moving with the truck. So in other words, the ball is going to be moving at a constant velocity because that's Newton's first law. An object in motion stays in motion. There's no outside forces acting on the ball in the x direction. So the ball should move with the truck. Okay, and you guys clearly see that here. So the ball is moving at the same speed the truck is going in. Now, however, is the motion of the object staying constant in the y direction? No, it is definitely not staying constant in the y direction. In fact, if you look, it's slowing down as it moves up. Then at the very top, it comes to a stop, and then it starts coming back down. And while it's coming down, it's speeding up, right? That's because of gravity. The force of gravity in the x direction, the force of gravity in the y direction has no impact on motion in the x direction. The two are completely independent of each other. If there's one thing that you guys understand on today, is that you understand that point, because we're going to elaborate more on this when I see you guys in class on Wednesday. But the important thing is, I want you guys to know that the x and y components are definitely independent of each other. So that's what causes this curved path here. Okay, Jeremiah, does this example make more sense when you look at the?
Yeah,
Yeah.
because I was actually
Yeah. So you see what I mean when I say how, like, if you throw a ball straight up, it's going to always stay above the moving vehicle or the moving object. Like, so hopefully that makes sense now. Okay. All right, and like I said, we're going to elaborate more on this concept in the coming days. Okay. Last thing that I want to do today, basically what I want to do, I want to pull up that PDF file that's in Schoology, and I want to work out several examples with you all. Okay, I want to work out several examples with you guys, so that you guys will be ready to do the assignment as soon as class is over. Okay. So in this particular assignment, guys, what we're going to be doing, we're going to be looking at different situations, and we're going to be comparing various projectile motion situations. Of course, we're going to be looking at different things, but we're just going to be making some comparisons here. And this is going to be pretty much the bulk of your assignment when I post it, comparing two or more situations. And of course, I'm going to kind of skip around here. I think I want to start off by looking at number 18. And again, you don't have to write anything down. Just be sure you're understanding the concepts. Guys, if you are in Schoology, you will notice that I posted a link to a projectile motion simulation. Use this link to help you with the assignment if you get confused on something. So, and I'm going to show you guys how this link works. Okay, so, if you click on the link, and I want to open it up in a separate tab. So once you click on this link, you want to click on this right here that says lab. And then you can use this to help you work on your assignment. For example, look at number 18. On number 18, we're going to be comparing three different scenarios. Situation A, situation B, situation C. Notice in every situation, we launch a projectile at the same velocity. So they're all launched at a speed of 10 meters per second. However, they're launched at different angles. One is launched at 45 degrees, one is launched at 60 degrees, one is launched at 30 degrees. Someone tell me, which one do you think will produce the greatest range? The one launched at 45, the one launched at 60, the one launched at 30. Can y'all tell me in the chat box? Okay, Stephanie says 60. Anybody else got any other guess? Which one is going to go the furthest? Jeremiah, you also say 60? Okay. Well, let's see, guys. So Angelina also said 60. Let's see which one is going to go the furthest. Okay. So along the side here, I can change the speed by which I can launch my projectile. So here I have a cannonball. Okay. So guys, we're going to start off with a 30-degree angle. Okay, so I'm gonna launch my cannonball from a 30-degree angle. Okay, notice how far the cannonball went. Okay, let's compare that to a 45-degree angle. Okay, so 45 degrees. Okay, let's launch my cannonball. Okay, notice how far it went there. Now let's compare that to a 60-degree launch. So let's launch it there. Someone tell me which one had the greatest range, the 30-degree, the 45-degree, or the 60-degree? uh, uh, thank you, James. Angelina, it was 45. uh, but yeah, James, it's 45 degrees. So 45 degrees produces the greatest range. So yeah, guys, that's something I want you guys to remember. Whenever you're launching multiple projectiles, the one that is launched from 45 degrees is what's considered the sweet spot. 45 degrees is going to always produce your greatest range. Okay, assuming all the speeds are equal, 45 degrees is going to go the furthest. Okay. All right, so let's keep moving, keep going. So I'm gonna clear my screen here. Yes, Angelina, 45 degrees is always the sweet spot. Yeah. So between launching something horizontally or launching something, launching something from an angle all the way up to 90 degrees, 45 degrees is the sweet spot. Angelina, it's gonna, that's the only one that's gonna produce your greatest range. You know, between 0 and 45 degrees. Yeah, between 0 and 90 degrees. Between 0 and 90 degrees, 45 degrees is going to produce your greatest range. You're welcome. Yeah, that's going to be your sweet spot. Let's look at some more situations here. Let's see, which one do I want to do now? Let me see. Guys, look at number 9. So on number 9, we're going to be comparing two situations. But here, we're not going to be launching our object at an angle. We're going to be launching our object straight up. So in situation A, we launch an object with initial velocity of 4 meters per second. Here in situation B, we launch an object with an initial velocity of 8 meters per second. Which one has the greatest maximum height? Situation A or situation B? Yes, Jeremiah, it is definitely situation B. Okay. And of course, guys, you can always compare that by going here to your simulation. You can basically just, aim the cannonball straight up, okay? And you can compare two different velocities. So for example, I'm going to start off with an initial speed of 12 meters per second. Okay. Guys, look how high the cannonball goes there. Now, what happens when I increase my initial speed? Let's say I increase from 12 to 15 meters per second. Look how high it goes there. So notice the greater speed gave the greatest height. Okay. All right. So that was an easy one. Okay. My screen. Let's see. Guys, look at number 2. Number 2 may be tricky for some of you guys. Look at number 2. So we have two situations, ball A and ball B. But notice, guys, in this case right here, they're both launched with the same speed, but A has a smaller mass. So, guys, someone tell me in this case, which one has the greater height? Or will the heights be the same? What do y'all think? This is a tricky one right here. Stephanie, Jeremiah, Angelina, y'all both say A. Now, it turns out that's not it's not a bad guess because a lot of people guess A, but it turns out that the correct answer is this. They both go the same height. Some of you guys may be thinking, well, Mr. Taylor, that's weird because A has a smaller mass. Okay, but yeah, I'm explaining right now, Angelina. Remember, Angelina, what did I say last year? Anytime two objects are launched here on Earth, and assuming we're ignoring air resistance, Angelina, what is the acceleration of both objects? What is the acceleration of gravity? Angelina, you know this. Yes, ma'am, 9.8 meters per second squared. So remember what I said last year? The acceleration of gravity does not depend on the object's mass. It does not matter how big or how small the object is, the acceleration will always be 9.8 meters per second squared. Okay, so since both objects was launched with the same speed and have the same acceleration, they're going to reach the same height because mass does not matter. Yeah, mass has no impact on the acceleration of gravity. Here on Earth, the acceleration of all objects is 9.8 meters per second squared. Making sense now? All right, awesome. Right, because think about it, Angelina. Gravity is acting on both of them, and gravity causes both objects to have the same acceleration. I know it's weird, but that's how gravity works. It's weird, but that's how the acceleration of gravity works. Um, um, any questions on that? Let me see. Gravity needs to get its life together. Angelina, do you like doing this better? Or you prefer to work? Or you prefer to do math? Or you just won't like talking about concepts? You like no math for me. Stephanie, you said it doesn't make sense. Stephanie, the important thing is that the acceleration is 9.8 meters per second squared for both objects. Both objects have the exact same velocity and the exact same acceleration, so they're going to go the same height, right? Because think about it. Both objects are slowing down at the exact same rate, so they're going to reach the same height. Okay. I know that's weird, but that's just the way it is. Yeah, physics just takes exposure. It just takes exposure. um oh, and Stephanie, if you're working on the homework and you're unsure on something, you can always go right here to the simulation. You can try this out. Watch. I want you to watch this, Stephanie. We're gonna do the first situation. But Stephanie, here I'm going to have the mass somewhere around 15 kilograms. Okay, so I'm going to launch the object. Okay, notice how high it goes. Okay. Now, Stephanie, let us compare that to the situation here where I'm going to change the mass from 15 kilograms to 30 kilograms. Okay. So notice I doubled the mass, more or less doubled the mass. Now watch what happens when I launch the ball again, Stephanie. So I'm going to launch the cannonball again. Okay. Notice how high it went. It went just as high as before. So the mass had no impact on how high it goes. Okay. So again, Stephanie, you can always use this website here to compare the two situations whenever you're working on your homework. Okay. If you're confused. All right. Again, guys, I'm just going to do a few more. I'm not going to do all of these. I'm just going to do enough to where you guys get the point. Okay, let's look at number 8. So I have two balls launched with the exact same initial velocity. However, ball A is launched from a higher height than ball B. So which one hits the ground last? Ball A or ball B? This should be an easy one right here, guys. Which one hits the ground last? Ball A or ball B? Remember, ball A is launched from a higher height. Yep. Ball A was going to hit the ground last. Thank you, Stephanie. And that should make sense, right? Because it has a greater vertical displacement. So since it has a greater distance it has to travel, it's going to take longer to hit the ground. Okay. Let's see. Let's look at some more. Look at number 3. This one should be easy. Which one has the greatest range, ball A or ball B? Notice they're both launched from the same height, but ball B has a greater speed than ball A. So which one is going to go the furthest? Which one has the greatest range, A or B? What do y'all think on this one? Yes, Stephanie, ball B. You are correct. Exactly, because think about it. If it's launched with a greater speed, that obviously must mean it's launched with a greater horizontal force. So it's going to travel further. It's going to be in the air longer. Okay. I'm sorry, it's not going to be in the air longer, but it's going to go further. That's what I'm going to say. So it's going to go further. All right, so let's keep going. And I'm just going to do a few more. Let's look at number 4. Okay. Number 4 says we have two objects. They're both launched with the same initial speed of 4 meters per second. However, ball A is launched from a higher height than ball B. Which one has the least range, A or B? So, in other words, which one is going to land closest to the table, ball A or ball B? Which one is going to land the closest to the table, ball A or ball B? Stephanie says ball B. Okay. Well, let's see. Guys, remember, you can always use this website right here to compare situations. And guys, what I like about this website right here, you guys see the platform? Check this out. You can actually raise the platform or lower the platform. So I'm gonna compare two heights. Let us compare a height of 8 meters. So, and again, the speed is 15 meters per second. So I'm gonna launch my cannonball. So guys, notice how far my cannonball went there. Okay. Now let us compare that to a lower height. So if I compare that to a lower height, again, is keeping the speed the same, and I launch my cannonball. Okay. So Stephanie, you are correct. The lower height had the smallest range, right? So the higher height clearly went further. So on number 4, which one is going to land the closest to the table? Is ball B. Ball B has the least range. Okay. All right. I'm going to do a few more. And again, I'm kind of skipping around. Look at number 20. Which one is going to hit the ground first? Well, notice, guys, they're released from the same height. They both have the same speed. Even though they're different masses, that doesn't matter. The acceleration is going to be 9.8 for both of them. So clearly, they're going to hit the ground at the same time. So 20. So pretty much everything is equal for both of them. Obviously, mass does not matter. Guys, in all of these situations, mass will not matter. Um, if everything else is equal, you can guarantee that they're going to hit the ground at the same time. Okay. Um, guys, look at number 17. Number 17 says, which has the greater acceleration? And they're talking about the vertical acceleration. What do y'all think? Which one has the greatest vertical acceleration? Is the acceleration the same for both of them? What do y'all think on number 17? For number 17, which one has the greatest vertical acceleration? Or are the accelerations the same? No, Devin, remember what I said. Here on Earth, the acceleration will always be 9.8 meters per second squared. So the acceleration of both objects is the same. Guys, please remember that on this assignment. Anytime, yes, Angelina, it's the same. Anytime it asks you about acceleration on any of these problems, here on Earth, the acceleration is going to always be 9.8 for every situation. Okay. All right, I'm going to just do two more, and then I'm going to let you guys go. Number 1 says, which one is going to hit the ground first? Okay. Hopefully it should be the case that, obviously ball B is going to hit the ground first, because think about it. Not only is it slower in height, but notice ball B is also released with this much smaller velocity. So ball B is not going to be in the air as long as ball A. Okay. I'm going to do one more with you all. Okay. Guys, let us look at number 29. This is the last one we're going to do. Which one has the greatest maximum height? So in other words, height is, we're looking at the vertical direction. Range means the horizontal direction. Height means the vertical direction. Which one has the greatest maximum height? So they're all launched with the same speed, but we're comparing three different situations. We're comparing three different situations. We're comparing one launched at 45 degrees, one launched at 60 degrees, one launched at 30 degrees. Okay, you guys say 60 degrees. So let's see. Okay, let's reset everything. Bring down my platform. Okay, so this is 30 degrees. Okay. 45 degrees. And of course, 60 degrees. And yes, Stephanie, yes, James, you're correct. 60 degrees produce the greatest height. So, situation B. All right, any questions regarding these projectile motion comparisons? Any questions? I did, Jeremiah. The link is already in Schoology. Like, it's right. Like, if you go to the folder for today, it's right here. It says link to projectile motion simulation. Yeah, it's already there. And so yes, use that link to help you out with the homework. Okay, there are 16 questions, all multiple choice. Okay. All right, guys. If you did not get an opportunity to fill out the attendance form, please do so now. Okay. All right, guys. Let Let me stop recording the video.